welcome to my channel. Let's learn the algorithm together. Today we will take a look at the 938 range sum of a binary search tree. And what is this problem talking about? We'll be given the root node of a binary search tree and two integers low and high, and then return the sum of the values of all nodes with a value in the inclusive range, low and high. So what is this talking about? Like, we have a binary tree here, and it is like 10, 5, 15, 3, 7, and also 18. And now we have the ranges, like the low is 7 and the high is 15. And from this tree, which nodes are false in this range, right? And we can see that is 7, 10, and 15. So that we added up all these numbers, 7 plus 10 plus 15, and then equals to like 32. So that's what we want to get, and then return this value 32. And we have a further look at the example 2, and that would be like 10 and 5, 15, and then go 3, 7, 1, 6. Yeah, so probably 6 here, 6, and 13, 18. So that would be like the tree. And what is the range of it? The low is 6 and high is 10, which we have to search for the nodes which falls in this range, right? And we can see it's the node 6, 7, and 10. And that's it. So now we add it up, like 6 plus 7 plus 10, so it equals to 23. So that's what we should return. And now how we are working on this problem, right? There's no doubt that we are using like BFS or DFS to help us to search this tree and find all the nodes falls in this range. And the first thing is like we may use BFS or DFS, but which we want to choose. So this problem, like, do we care about the level or something else? Like this, usually like we use BFS is because we care about the level, there is depth and height or something like that, right? Like level, depth, or height or something like that. Do we care about that now? No. So we are not choosing BFFs this time, and we want to choose the DFS. And why? So first of all, we also have to know some probability or probability characteristics the BST has, the binary search tree. It means that the node, for example, for this node, the left child is always less than the root, and the right child is always greater than the root node. So from the whole tree, we can see that 1 is always at the most left, and then we can see 1, 3, 5, and then go to here 6, 7, and then 10, because the right child will always greater than its root nodes. So the 6 will definitely like be here instead on its left side. It means that for a binary search tree, if we're using in order traversal, we will like have an ascending order. We will get ascending order. So for this tree, will turns out like to be 1, 3, 5, 6, 7, 10, 30, 15, and 80. Like what is the in order traversal is we go right first and then work on the current level. The current root nodes. And then we go to the left of the root nodes. Oh, my bad. Is we go to the left first of the nodes. And then we go to the right of the node. So that will be our in order traversal, how we work on that. And how we apply this to this problem, like when we are traverse these nodes, we don't have to like go through all of them. When we are compare this like the root node, if the root node is already like, for example, like for the current nodes, if the current node is not in the range, right? We don't have to go to the left side. So only if the node is less or so if it is equal, we also have to, we don't have to go to the left side, because if this one is equals to the lowest boundary, it means that we will definitely work on this node at the current nodes step. So only the node is less than our lower boundary. Low boundary. Then we go to the left side to continue to do the explosion for these nodes. But now, like as I said, 5 is already not at this boundary, so we don't have to go that side. And for the right side is also like only if the node is like it also in the range of this, or probably can say like this 15 is in the range. It's greater. It is equal to 15, so we also don't have to go to the right side. But if it is greater than the 15, which is the high, then we go right. But now my question is, what we do at current level, right? So for a current level, what we gonna do? Because this problem is like we collect all the nodes that fall in this range, we are doing a assumption, right? So what we want to do is, for example, like if I'm the parent node, I'll definitely ask my left child like, hey, so now what's your sum of it, right? So for the node 5, it doesn't have the no idea, so he will try to ask his left child. But since his left child is already like not in the boundary, we won't go to left, so there's no need we ask them. So it just asks its right child. We can see we don't ask them. Ask its right child, and the right child has no idea. We'll continue to ask its left child first. So the left child will tell him like, so now how much I have, but also left child will continue go to the next is probably no, right? But if it is no, we don't have to ask the left, so we just work on current level. So when it it will got like how much it has, right? So it will tells back like, yeah, I have already sum. The sum is 6, and for the 7, it got 6 already from its left child, and also want to get from its right child, and then it will add it up like 6 plus its current 7, and then it returns to 13. So the 5 is also not following the range, so it won't add it up. So it just return like 13 and tell the root node like, yeah, I got 13 from my child, and also I consider myself. And then like for 10, after it got the result 13 from its left child, it go to ask its right child, how much do you have? And 15, because the 10 already, I mean the 15, the 10 is already like meet the range, so there's no need to add its right child, because we also said this. If already it's not high, then we don't have to go right. But now it means that we also can add it like, or we can, because when we are going to the root node, we also can say if the node of the right is not only not now, we will go, then we go right, and so does the left side is like only the node of the left is not now, then we go to the left. And for the current is like, because we want to get is the sum of the left and right, so we definitely will have the integer like sum. At first it's 0 because I have no idea, so that's why I ask my left child go left, and then sum plus the then we'll sum add it go left, and also we will add it up the sum we got from the right. And after that we also have ourselves, right? So if the current node is also following the range, we also add it to it. Or probably here we can say if our current node is greater than current node value is greater than low, and as well as less than high, only that we will add it up the current node value, or we will just add 0 because we don't want to get it. And after work on this, we can continue to ask our left and right child to continue to do the calculation. And after that, we return our sum to our parents, like saying, hey, how much do I have now, right? And also, this is what we do for sums up. But what if like we already go to the leaf nodes? Yeah, so no worries about that. Even we go to the leaf nodes, we already get the sum, and then try to, because we the left node is, now we don't go left and also we don't go right, and we just return the sum. So this is how we do like using like DFS to work on this problem. And of course, this is how we are go through a simple example like this. If this is the 10, at first we already like it falls in the range, we are adding up to 10, and then we go to the left side and 5 is not there, so we go to the right side, we add, because 7 is here, we will add 7 from here, we go to the right side and add 7 here, and then we'll continue. But because it's not now, so we don't go to left or right and just return 7 back. and then we go back and return 7. And this is how we got from the left side. And then we go to the right side and got 15. And after that, we sum it up like 10 plus 7 plus 15. So we return the sum. Finally, it's 32. And for this problem, like what is the time complexity? So because we are using DFS, and it means that it's the OH. H means the height of this tree. Can say height of this tree. And what is the space? The space is because we are, oh wait, my bad. The space is the OH, and H is the height of the tree because we are using the stacks to go to each level to keep track of it. Using a stack, something like to remember it. And for the time, the worst case is all the nodes are falls in the range, so the n means the number of the nodes. But of course, this is the worst case. And if it's like the range is just the root node or just like this few nodes, we don't have to go through the whole tree. So definitely like less than the ON. So this is the space and time complexity. And now let's move to the coding part. And as I said, like at first I will have a sum here, and we are evaluate whether the current root node is in the range, right? So like this, root dot value. If it falls in this range, root dot value less than the high. If it falls in it, we will equals to the root value, else we'll just treat it as 0. And then we start to go to the left side, but only it meets our condition, like the current root value is less than the low and the node dot root dot left is not known. Then we are going to our left side and wait. So the sum will plus the left side root dot left and low and high, something like that. So this is the left side, and also about the right side is the root is greater than the high and the right is not known, and then we can add it up it, and after that we just return the sum we got. And now let's run it. Oh no, so what's going on? And the output is 10, but we expect it is 32. So for go to the left and right, and we are consider like if the current node is in the range, we will have these values, right? So for like 10 is in the range, got it. So now the root node is, oh wait, it should not be like less than low. It means that it is still greater than low. Then we will go to the left side, but if it's also equal to low, we don't have to. And this is we are less than high, we can go there. Yeah, that's the current case. So now here the problem is, it's not less than low, it should be like greater than low, and also this is like less than high. So only if the root node is still in the range, we can like continue to go left and go right. Now let's submit it. Cool. Now all the tests passed. So this is how we are working on a binary search tree. We have to know like what is the binary search tree. When we are working on the in order traversal, we will get a ascending order of each nodes. And also we have to know that when we are comparing the current node, we know all the left side nodes are less than the current node. So which means that we can do some like trim of the tree. So once the root nodes values are all less than low, we don't have to go to the left side. So that's the right side. If the node's value is greater than high, we also have, there's no need to go to the right side. So it will help us to save some time. And this is how we use the DFS to work on this and why we choose DFS, not BFS. And if you think this video helps you, please give me a thumbs up. That would be great encouragement for me. And thanks for watching. See you at next video. Bye.